Here's the nightmare everyone has. You're in an elevator, the cable snaps, and the car plunges down the shaft. Except that almost never happens. Not because the cables are strong, though they are. The cable isn't even the thing that makes an elevator possible, and a real freefall is nearly impossible by design. Two inventions did it. One means the motor barely lifts anything at all. The other, from 1853, means the instant a cable goes slack, steel jaws clamp the walls of the shaft and stop the car cold. That second one is literally why we can build skyscrapers. Let me show you. Start with what's actually up there. On top of most tall buildings sits a machine room, or these days a compact motor tucked into the shaft itself. From it, steel ropes run down, hold the car, and here's the part people miss. They don't just hold the car, they loop up and over a grooved wheel and back down the other side, where they connect to a heavy block of steel called the counterweight. So it's not a car hanging off a cable. It's a car and a counterweight tied together over a pulley, like two kids on a seesaw. That one design choice changes everything about how the machine works, how much power it needs, and why it's so hard to make it fall. The cable is just the rope between the two riders. It's important, but it is not the trick. The trick is what's on the other end. Look at the wheel at the top. It's called the sheave, and it has grooves cut into it. The steel ropes lie in those grooves, and a motor turns the wheel. That's it. The motor doesn't reel the cable in like a fishing line. It just spins the wheel, and friction between the ropes and the grooves drags the ropes along with it. Turn the wheel one way, the car goes up. Turn it the other way, the car goes down. This is called a traction machine, and the word traction means grip. Now here's what's strange. That motor is far smaller than you'd expect for lifting a loaded elevator car up 40 floors. A car full of people can weigh a couple of tons, and yet the motor sips power. It should be straining. It isn't, because the motor is almost never lifting the full weight of anything. That's the counterweight's whole job, and it's the most elegant part of the entire machine. Here's the elegant part. The counterweight isn't random. It's engineered to weigh the same as the empty car, plus about 40 to 50% of a full load. Think about what that does. When the car is about half full, the two sides of the seesaw are almost perfectly balanced. The motor is barely moving weight at all. It's just nudging a system that's already in equilibrium, overcoming a little friction and a small difference. So the motor doesn't lift a 2-ton car. It lifts the difference between the car and the counterweight, which is small. When the car is heavy, the counterweight helps pull it up. When the car is light, the counterweight's extra mass helps pull it back down. Either way, the motor only handles the leftover. That's why you can move tons of people up a skyscraper on a motor that, relatively speaking, is modest. Take the counterweight away, and you'd need an enormous engine and enormous cables for every trip. The counterweight is the reason tall elevators are even practical. But balance is about efficiency. It is not what keeps you safe. So what happens if the rope actually breaks? First, the cable is not a cable. An elevator hangs from multiple steel ropes running side by side, typically 4 to 8 of them. And this is the key number. Each individual rope is built strong enough to hold the entire fully loaded car by itself. All of them together give a safety factor of something like 10 to 1. So one rope fraying doesn't drop the car. The others carry it, and inspectors catch the worn rope long before it matters. For every rope to snap at the same instant, you'd need something so far outside normal operation it basically doesn't occur in a maintained elevator. The famous cases in history are almost always something else: a rope snapping under a freak condition, or sabotage, or catastrophic neglect. And even then, we don't rely on the ropes to be the last line of defense. Because a mechanic in the 1850s assumed the ropes would fail, and built the machine that saves you when they do. Before 1853, elevators existed, but only for freight, because everyone knew the rope could break and no one would risk their life on one. Then a mechanic named Elisha Otis had an idea. Don't just make the rope stronger. Make a brake that grabs the moment the rope lets go. In 1853, he started his company on it. And in 1854, at the New York World's Fair, he stood on an open platform high above a crowd and had an assistant cut the rope with an axe. The platform dropped a couple of inches and stopped. He tipped his hat. all safe, gentlemen. That single demonstration is why we trust elevators, and it's why we started building up instead of out. Here's the mechanism. The car runs between two vertical steel tracks called guide rails. Bolted to the car is a set of spring-loaded steel wedges, the safety gear. As long as the rope holds tension, those wedges stay retracted. The instant tension is lost, springs drive the wedges outward against the rails. And the geometry is self-tightening. The faster the car tries to move, the harder they bite. The car doesn't fall. It grabs the walls and stops. The taller our buildings got, the more everything above the lobby depended on that one idea. But the brake needs to know when to fire. That's a separate device called the overspeed governor, and it's beautifully simple. A small pulley near the top spins a separate governor rope that's clipped to the car, so it turns at the exact speed the car moves. Inside the governor are weights that swing out as it spins faster, exactly like the spinning ball speed regulators on old steam engines. Below normal speed, nothing happens. But if the car ever moves faster than it's allowed to, usually around a quarter over its rated speed, those weights fling out far enough to trip a latch. That grabs the governor rope, and the yank on that rope is what fires the safety gear into the rails. So stack up the layers. The counterweight means the car isn't just dead weight waiting to fall. Multiple ropes each hold the whole car. If they somehow all failed, the car starts to speed up. The governor senses it in a fraction of a second and clamps the wedges to the rails. And if by some impossibility the car still reached the bottom, the pit has one last catch, a heavy spring or an oil-filled piston there to absorb the final impact. For an actual free fall to reach the ground, every one of those independent systems has to fail at the same moment. That's why it essentially doesn't happen. So it's incredibly safe. That doesn't mean it's flawless, and the honest trade-offs are worth knowing. Getting stuck is common, and it is the safety systems doing their job. If a sensor reads anything wrong, a slightly open door, a power dip, an odd speed, the elevator's default is to stop and hold, not to keep moving. A stuck elevator is a working elevator being cautious. It is basically the safest place in the building. And the waiting. Why does rescue take so long? Because the rules say a trained technician has to bring it to a floor and confirm it's locked before the doors open. Forcing your way out puts you in the gap between the car and the shaft, which is the one genuinely dangerous move. The doors get their own guard. That invisible beam or grid of infrared sensors across the doorway means the doors reverse if anything breaks the beam. Older elevators used a physical bumper that had to touch you first. The light curtain reacts before contact. And not every elevator even works this way. Tall buildings use the traction and counterweight system we've described, increasingly as gearless, machine-roomless designs, where a compact high-torque motor lives right in the shaft and drives the sheave directly. No separate machine room, no gearbox. But short buildings, 2 to 5 floors, often use a completely different machine, a hydraulic elevator, where a pump pushes fluid to drive a piston that shoves the car up from below, and gravity lowers it. No counterweight, no overhead machine. It's cheaper for low rise and slower, which is why you feel the difference in a small building. So let's kill the 2 big myths. Myth 1, the danger is the cable snapping and the car free falling. In a maintained elevator, that's the failure the entire machine is built to survive. Multiple ropes, each rated for the whole car. An overspeed governor watching every second. Spring-loaded wedges, ready to lock the car to the rails the instant tension is lost. A buffer at the bottom as a last resort. Free fall isn't the risk you should picture. It's the one thing the design is obsessed with preventing. Myth 2, a big strong motor is heaving that car up the shaft. It isn't. The counterweight does the heavy lifting by balancing the car, so the motor only nudges the small difference. Grip on a grooved wheel moves the ropes. Balance carries the load, and a mechanical tripwire stands guard the whole way. That's the whole thing. A car and a counterweight over a wheel, so the motor barely works. Several ropes that each hold everything, and a 170-year-old brake that trusts the rope to fail and catches you when it does. The cable was never the point. The catch was. Subscribe to Whambox for more how does it actually work explainers.